Thank you, Jim. So I'm visiting this week from Indiana, as Jim said, and I'd like to talk this week and next week about power spectra and how to infer processes from power spectra. And by a process, I hopefully want to be able to express that in terms of an epsilon machine. Today, I'm going to concentrate on the problem in a more abstract sense. And on Thursday, I'm going to apply it to actual materials. So today, a lot of the stuff that we'll talk about will carry over to the material case conceptually, but we'll find there'll be a lot of details that we'll have to tinker with and bother, because nature tosses us a few kind of curveballs and makes a problem in reality in the material case a bit more interesting than this. But this is a nice way just to get into the basic ideas and the basic concepts of what we're going to do on Thursday in a bit more detail. I'd like to think of today's lecture sort of being in two parts. The first part is talking just a little bit about power spectra, and then the second part is going to deal with inference, and I'll show you an algorithm where one can infer processes from power spectra in the second part. So let me motivate this just a little bit. Before I even tell you what a power spectra is, let me just remind you of some things that you've seen before. So this is just a learning channel. This is a slide I have stolen from Jim shamelessly. And just reminding you that there's some system here that's doing things in a box. You can't look in the box. Can't see what's in the box. And it puts out some type of signal, and then we want to be able to build a model of that model just from the data there. And Jim has talked about that. The subtree merging method is one way to do it. I believe Chris talked about Bayesian inference, and that would be another approach that you could take. So there are various ways of doing this, but what's going to differ here is that we're not going to actually have access to this signal. In fact, sometimes nature processes the signal for you and you don't get to see it. And at other times, you might actually want to you might actually want to process the signal yourself and think of what the power spectrum would look like, because it can tell you some interesting things. But as far as reconstruction is concerned, you always want to use the raw data if you can. So the modified learning channel that we have now is, just as I said, but we have some signal processing in here. And what happens is this guy creates data, and we don't get to see the data that comes out. It goes through some type of processing, and then from this guy right here, we have to, we want to try to infer the process that's going on. But this little chart up here, because a power spectrum is going to look like a graph. And a power spectrum is a Fourier transform, is a discrete Fourier transform of a sequence series that one has, and the interpretation of a power spectrum is this, and this helps me keep it straight. If you have, so I'm from a physics background, and I think of this in terms of physics. If I have a wave source that is composed of many different frequencies, then I can look at the power spectrum, which is going to be a function of frequency, and that will tell me where the most of the energy, or where most of the wave action is occurring. And that might be interesting in and of itself, just to look at. A little bit more formally, sorry, things dragging around. A little bit more formally, I want to define a power spectra of a discrete series. I need to start off with a discrete series, so I look at this guy right here, and I just assume that I have a standard sequence. I'm going to restrict my attention to the binary case, but there's no reason why it has to be binary. It could be an alphabet of significantly larger. The discrete Fourier transform, I just define it to be this guy. And so I just multiply each symbol in the sequence by this exponential, and I do the sum, and I divide by the square root of n, and that's just for normalization. There's nothing magic there. And when I define the power spectrum, I just take the absolute square of this. You'll notice that since I've stuck an imaginary term in here, the Fourier transform of the sequence can in general be complex. But when I do this process right here, when I square it, I'm going to lose all of that phase information, is what we say, that's associated with this with this e to the I term. And this is, this actually ends up causing us some difficulty, because this step right here where I lose information. And that means that it's going to be harder to reconstruct the process if I just have access to the power spectrum and not to the symbol sequence. What I'm showing you today, just let me go ahead and mention, is sort of it's an intuitive way of looking at the problem, and it's a good way to give you a basis for both today and tomorrow. But there's much more elegant techniques for doing this. Recently, Paul Reichers, who many of you I think know, and Jim have shown that you can actually do most of what, or a great deal of what I'm going to do today, using a Z transformation. And while this algorithm suggests that one can just calculate it just by numerically putting it on a computer and just doing it, in fact, you can do a lot of this analytically. And that's very, very nice. It's nice conceptually. And later on in the lecture, I'll show you places where, just from a purely calculational point of view, it's going to be nice. It really is a much better way of doing it, but this gives you a very good idea of the nuts and bolts about how it works. So we know what a power spectrum is. A correlation function, well, I can rewrite the power spectrum just by putting it into the previous expression and squaring it. I get something that looks like this. And now I want to rewrite this sum. I can get rid of the imaginary part by a trigonometric trick, and I get something that looks like this. And then finally, I can define one of these sums to be this guy right here. And when I do that, I end up defining a quantity that I call the two-point correlation function. Actually, as I go through the lecture, this quantity is not the quantity that I'm going to be talking about, but I'm going to talk about a related quantity to it. But the correlation function is nice because it gives me some information about how layers, what kind of knowledge layers have, or not layers, I apologize, I'm getting ahead of myself, what kind of knowledge symbols have when they're separated by a certain distance. And I'll give you a little bit better interpretation on the next slide. Do you have any questions up to this point? Have I been crystal clear or opaque or just moderately so? Please feel free to interrupt me at any time if you have a question. I'm very happy to address. So we can rewrite the remaining sum, and it looks like this. So the power spectrum comes in this nice form. It's just a sum over, it's just a single sum. It involves the correlation function multiplied by this trigonometric function. So this is nice. Clearly, this is always going to be real. There's no imaginary part any longer, and in fact, it will always be positive. Now, here's a nice thing. We're going to take significant advantage of this. I have a function expressed as a series of cosines. I can pull the Fourier trick and multiply both sides by a particular by a particular cosine of a particular frequency. I can then do the integral, and one of those terms will pop out. And the term that I end up with for one of those frequencies is going to look like this. And so I can determine what the correlation function is for any value of n just by performing this integral. This is just a very standard mathematical trick or process that one does. So if I'm given the power spectrum, I can find all the correlation functions. I can get them all very quickly, very easily. That's not a problem. Now you'll notice that when I do this, I've integrated from 0 to 1. I, in fact, did not have to integrate from 0 to 1. I only had to integrate over a unit interval of frequency. I could have integrated from 1/2 to 1.5, just so long as the delta interval is 1. This doesn't have any particular consequence today, but on Thursday we'll see that this actually turns out to be very helpful when we deal with real materials. So this is a general result. This, in general, power series can be related to correlation functions in this manner. And finally, I don't really want to work with this C sub n, and this is really a matter of taste. This is anticipation of Thursday. I want to work with a related quantity, and I'm going to refer to this as the correlation function. And from now on, whenever I say the correlation function, I really mean Q sub n. And it's just related to this guy linearly. And this, in terms of, if I express it this way, then this guy has a very nice interpretation. This guy simply means what is the probability that two symbols at a distance of n are the same. So if I have a symbol here, Q sub n just means what is the probability that some distance away I have the symbol that is of the same kind. So that's a nice physical interpretation for it. Power spectra, I don't intend for this classification scheme to be exhaustive, but power spectra can be broken down into a couple of three classes. One is pure point. For some processes, it turns out for some processes that there will be parts of the spectrum that are point-like, and what this means is that as I increase the length of the sequence, the number of terms I have in my sequence, then the power spectrum at a particular frequency will sometimes grow as the square of the number of terms in the sequence. This gives rise to something that we call, we think of in terms of delta functions. They're really points, and they're very, very sharp in the diffraction spectrum if we look at them. Another possible growth rate with the length of the sequence is if it grows linearly. Linear growth rates tend to tell us that there is some type of disorder in the process, that we're looking at something that has a positive, that has a non-zero entropy. And in terms of the physical case, it's the second one, the continuous case, is going to be the most interesting. Because when we relate this to looking at materials and looking at disordered materials, we'll oftentimes see diffraction spectra, which are just power spectra that scale is in, and those end up meaning that we have disordered materials. Another possible scaling of this guy is singular continuous, and this guy scales with some power between 1 and gamma, between 1 and 2. So it's sort of in between these two guys. This is a little unusual. I will show you an example a little bit later on called, I usually say Morse, but some people say the reverse, and then some people add Pruitt into the name too, but I'll call it the Morse sequence, that actually scales this way. Power spectra that look like this look very funny. They turn out to have fractal properties, and they turn out to be, when I show you one, you'll see that it looks really very, very different than anything else that I will have shown you. Questions? Sir?
So in the continuous process, would that be something where there's basically no correlation between
No. It could be, but there's no correlation. So I haven't been terribly, so in this column, this is the character of the power spectrum, what kind of power spectrum it is, and this is how it scales. It turns out that for the continuous case, that frequently what it does mean is that there is some type of entropy, so there is some disorder, there is some uncertainty in what's going to happen, but it doesn't have to be completely uncertain. There can be structure that underlies the process. So it doesn't have to be completely random. It can be somewhere in the middle between ordered and completely disordered.
So the labels here refer to, if you say continuous, you mean continuous with respect to frequency.
Right, exactly.
On the right side, you're saying if I pick a frequency,
yes,
roughly speaking, the energy there scales as you've given.
Yes. Yes, thank you. That's a much better way to say it. And there could be other behaviors. I've just pointed out the ones that are going to be important to us later on. If there aren't any questions, I'd like to just go over a couple of 3-4 examples of power spectra and correlation functions, just to give us an intuitive feel for what they look like, and it may help us build some intuition about when we see a particular process, what kind of power spectra would we expect to see from it, and vice versa. If we see a power spectra, what does it tell us about the process? The first guy I want to look at is a completely unstructured process. I'm calling this the random process. I'm assuming that what we have is just a single state, and this state with a probability of 1/2 can either go to a 0 or a probability of 1/2, it can emit a 1, and it goes back to the state. This is about as unstructured a process as you can possibly get. This is completely random, and this would be the case that you had just brought up. Well, when we look at the power spectra, first let's look at the correlation functions. The correlation functions are very boring. All they are is 1/2 for all of n. So what this says is that if I pick any two symbols in the sequence, if q is equal to 1/2, it says the probability that those are the same is going to be 1/2. So this process has absolutely no structure to it. When we look at the power spectra, we find that it is also completely flat. There's really not much you can say. All frequencies, you can look at it a couple of ways. All frequencies are present in equal quantities here. There's nothing that is preferred. I would now like to look at a process that's completely ordered. So I want to go to the other end of the spectrum, if you will, but spectrum in a different case. Looking at something that has no disorder in it. And this is going to be the period 1 process. And the period 1 process, written in terms of an epsilon machine, looks just like this. Again, it's a very simple process. It emits a 1 without fail each and every time. It has no memory associated with it. This is all that it does. So the correlation functions are particularly easy and straightforward. The probability of, if I pick one symbol, the probability that a symbol n downstream from it is the same. The probability, that probability is 1, because they're all 1s. That's the only thing we have in the spectrum. Now, something that I didn't mention earlier, but let me just go ahead and remind you that when I looked at the power, when I mentioned the power spectra, we noticed that it was in terms of a sum of cosines, and that it turns out that the power spectra, then the longest, the cosine with the longest frequency just spans a unit in frequency space. So it turns out that the power spectrum is it just simply repeats itself as I go to larger n. So I really only need to, if I go to larger f. So if all I really need to do is look at an interval from, let's say, 0 to 1 to get all of the information. All I really need to do is look at a unit interval in f, and any other interval will just repeat itself. So here I've actually made a choice. I've chosen to say that that when f is equal to 1, that I have this very large spike, and all of the power spectrum is completely located here. I could just as well have put that spike here or put them in both places, but I wanted to put all of the I wanted to put the spike here because if I put it at 1, it gives you a very nice interpretation. You can ask yourself, what is the period of this process? So if I think of period, I can ask myself the following question. How long does it take for the process to repeat itself? If I look at this process, how far do I have to go before it starts over again? And if I have just a sequence of 1s and that's all I have, it just, the period itself just turns out to be 1 because it's just the same thing over and over again. Another way of looking at it, let's leave it at that. So it has it has a period of 1, and it turns out that when I go to frequency space, that the frequency tends to be inversely related to period. So if this has a period of 1, then it turns out in frequency space that it has a frequency of 1, just 1 over 1. I could have just as well put this at 0. Mathematically, they are the same. It turns out that a lot of people will like to put it at 0 because this will be sort of a frequency equals 0, sort of a no frequency case. The next process I'd like to look at is one that's a little bit more structured, but is also a zero entropy process. And it's sort of the next in the line of what you might want to think of, and this is the period 2. And let me just remind you of what the period 2 process is. It's just a two-state machine. This is the recurrent portion, and it just simply repeats 1, 0, 1, 0, 1, 0. So there's never any ambiguity about what the next symbol will be once you know what the process is. A little bit of thought will convince you that the correlation functions have to look like this, that any two spins, any two symbols that are an even distance apart have to be the same. And if they're an odd distance apart, then they have to be different. So my correlation function just oscillates between 0 and 1 back and forth. Now, the period of this is a little bit easier to see here, but the period of this you would think is 2, because I go 1, 0, and I'm back to where I started, period of 2. And we see that all of the power spectrum is located at a frequency of 1 over 2 or 1/2. And I don't get any contribution to the power spectrum anywhere else. So, okay. Let's now look at a process that is a little bit unstructured, but it has some structure, but also has some entropy associated with it. And you've talked about this in class before. I'm sure it's called the golden mean process. And the golden mean process looks something like this. Let me just remind you that if the last symbol I've seen is a 1, then the next symbol is a 1 with probability 1/2 or a 0 with probability 1/2. However, if the last symbol I've seen is a 0, then the next symbol has to be a 1. What this does, particularly at this state, is it forbids any sequence that has 2 consecutive zeros in it. So it has some structure, but it's also considerably random. If we look at the correlation functions, they turn out to look something like this. It turns out that if we go that once we get for n, once we get like 10, 15 away, that these correlations they go to some asymptotic value, and in this case it happens to be 5/9. But there is a little structure when you're for symbol sequences that are close to each other. If we look at the power spectrum, then what we find is that we get something this is a continuous power. This portion of the power spectrum is continuous, and it also has a, I could just as easily have put this spike at the origin instead of at 1. Mathematically, they're the same, but it also has a discrete portion. And although I don't show it on this slide, this goes up to about 1100. If you'll notice on the previous slides that the power spectrum went to 10,000, and that's just because I chose a symbol sequence that was 10,000 in length. So if I'd chosen a longer symbol sequence, then this would have been, it would have simply been the number of layers. So this is what this guy looks like. It has a strong peak at roughly 1/2. And these guys, it turns out that it's symmetric about 1/2. And it looks like this. So from what I've said before, it would seem like that since I'm seeing a lot of the power spectrum is stronger at 1/2, then what I'm seeing is I should expect for this process to have a lot of, how do I want to phrase it? The wave action at period 2 should be large. And this is a period 2 process. And so, I'm sorry, this is a two-state machine. And so it does have a lot of period 2 character to it. So that's not completely unreasonable of an interpretation.
So why all the energy at the 1 though, at
The energy up at one of the spikes, we can actually, there's actually a really nice way to see that. If we go back to this expression and we look at P of F, then we find that when we calculate this guy, that if it turns out that there is a preponderant, that if the total number of sequences, the total number of symbols is not equally divided between the two, and in this case it's not, they with the golden mean, then in fact, as the correlation functions die off, and we saw this died off very quickly, we get a term here that just continues to add. And especially if I put in a frequency of either 0 or 1, then this cosine is always just going to be 1. And so I get this sort of residual term that just adds up.
Is that essentially where all the power ends up if it doesn't have a particular period to it? Like you always just treat it as like period 1.
So I struggled with this a little bit. When I wrote this down, since I wanted to give you the interpretation that the period and the frequency were inversely related, I put the spike here. In this case, though, I think what this is really, I think the better interpretation is this, is that at zero frequency, this is some type of zero order effect. The fact that there's an unbalanced number of zeros and ones, there's more ones than zeros, it means that this term is additive for a great portion of the sum, and it just gives you a delta function. If you move f slightly, it's a second fall. If you move f slightly, then this term will start to oscillate around, and those contributions will cancel out. But it's just at f equals 0, you get this cosine only being 1, and it gives you this additive quality. Paul, did you have another way to?
I just wanted to add that I think even if the probabilities of zeros is the same as probabilities of 1,
yes,
you're going to get a delta function if the expectation value of the values of the symbols is larger than 0. So even in the case of the fair coin that you have,
yes,
1/2, you have on average a certain amount of signal
yes,
that you see, and that can be considered as either period 1 or infinite wavelength, which is at the 0. So even in that case, you have a delta function at 1. If you have ones even more often, then you'll have an even higher delta function.
Actually, I don't think you do have. If we look at this expression, let me go back. Oh, that's way back. If I look at this expression for the power spectrum, then what I find is that when Q is equal to 1/2, it means that C is equal to 0. So it means that I put 0 in here for everything when I'm doing a completely random process. So this term actually never contributes at all. Now, if you're thinking in terms of the polytype case, in fact, that is true, but that's true because of mapping is a little bit different than it is in this case, I think. You do get those integer delta functions in that case, but in this case, you don't, actually. You're used to seeing a term right here that gives you a delta function, right? Or
I don't know. I'll have to think about it.
Your formalism with Z transforms may give a little bit better insight into what's happening. I could certainly believe that in coming up with this expression, that if you were to go through it carefully, that you would find that there were two terms that canceled out, and one of them was going to be something that gave you like a delta function at the origin or at an integer L. But it turns out that it is completely canceled out by this term, so you don't get it in this particular case. So This process is, as you all know, since I can just define completely what's going to happen with the next symbol in a probabilistic sense by considering only the previous symbol, then this is a first-order Markov process. So this guy is fairly simple.
Question.
Yes, sir.
So trying to interpret, I guess, a little bit more.
So
There's also in the golden mean there's f values
Mhm.
non-zero for a lot of different f values. So like at 1/4, can we kind of represent that as being like has period 4 characteristics?
Yes. What I would say is yes, that between point 2 and point 3, the fact that there is, relatively speaking to the other parts of the continuous part of the spectrum, that there's relatively little diffracted, there's relatively little, the power spectrum is relatively small. It means that if you're thinking about this being, if you're trying to describe this as a superposition, if you're trying to describe the process as a superposition of waves, some of which have a frequency of 1/4, that contribution would not be very large.
Okay.
Whereas the contribution at 1/2, the frequencies at 1/2 contribute larger. They're larger in magnitude. They're more prominent in the signal.
Okay. Okay.
The next process I want to look at is a process that cannot be represented as a finite order Markov process, even though it's very simple, or it looks very simple, and I'm sure that you've talked about it. It is the even process. And this is what the even system looks like. Now, there are a couple of interesting things to say about the even system. First of all, it has almost the exact same causal state structure as the golden mean, except that I've switched the emitting symbols from this first state, which I now call an A, from a 1 to 0 and a 0 to 1. So it looks exactly the same. Another thing to notice out of this guy is that the correlation functions, they die off very quickly. So this doesn't have a whole lot of structure at long distances. It turns out that this also goes to an asymptotic value of 5/9, the same as the golden mean. Now when we look at the power spectra, there's some interesting things to look here, to think about here. First of all, if you believe the interpretation that I have given you before, and I look at this guy and I'm saying, well, come on, I mean, it has sort of, has 2 states. Maybe I would expect something to be prominent at a frequency of 1/2, because it looks like sort of like maybe a period 2 kind of thing. I get exactly 0 diffracted intensity at, well, I'm sorry. When I calculate it, it's not quite 0, but it is very close. It could be, it's so close that I'm not sure whether it's numerical error or not, but here it looks like it's in fact 0. We also get at integer f, we also get this kind of delta function again, this kind of pure point contribution. And this guy is also, if I were to draw this out to the magnitude to scale, this guy would go up to about 1100 also, just the same as it did in the golden mean. I'm not sure why it goes to 0 here. I've thought about this a little bit, and I can't give you a good interpretation. I would actually expect just the opposite, and yet it doesn't. It seems to be that there's some type of cancellation that is occurring, or something. That is an interesting question. Why that happens? In the polytype case, in the material science case, we also see, when we look at these kinds of infinite memory processes, we also see cases where at certain frequencies, or in the material science case, it's going to be at certain inverse lengths. We also see this odd behavior where the power spectrum looks like it goes to 0, or almost exactly 0. So I don't know why it's doing this, and this is an interesting question, sir.
I'm just thinking, because it's an even process, you're always going to get an even number of 1.
You're always, exactly, the even process, so you're always going to get an even number of 1s.
So if you look out just 2 steps out from where you are currently, right?
Yes.
It seems like you would have kind of a minimum, because you're about to switch to the others. You're about to switch to giving a 0 instead of a 1 number of times. I don't know why it would be 0, but it seems like
Intuitively, you think it seems like it should be 0.
It should be minimum.
Paul has actually looked at this system in a little bit more detail using a Z transformation, and let me ask if...
I have a suggested interpretation.
Okay.
So again, I'll suggest that the only symbols that give power to the power spectrum are those that are non-zero. And so if you look at the system here, and also consider that a period 2 process would be of the form 0, 1, 0, 1, 0, 1.
Yes.
There's absolutely a restriction. The only transition restriction really enforced by human process is that you can't have 0, 1, 0, 1. So you should expect it to go identically to 0 at periodicity of 1/2.
But you could have things that are 1, 1.
Right, but that's not.
But maybe that's getting
that's
captured in another at another frequency.
Yeah.
Maybe that would be thinking 1, 1. You should really think just 1, and that's being captured here, and that would be a harmonic. Or maybe there's some kind of cancellation going on. I haven't thought about this, but let me. I don't think that I said this, but it was on one of the slides, and let me just remind you very quickly that when I actually have calculated. When I've actually calculated these sequences, I always take, I use a 0 and 1 because it's a lot easier, but I actually, whenever I see a symbol 0, the value I assign to that is -1. If I didn't assign, now that was a choice that is sort of arbitrary. I've chosen to make that choice. I could have chosen another. I could have chosen to just use a 0. But if I chose this to be a 0 symbolized by 0, then if I look at the Fourier transform of this of the sequence of pure zeros here, then the Fourier transform would be 0. So the power spectrum would be identically 0 everywhere. And if I did that, then this trick here of integrating over the power spectrum to find the correlation functions would be a little bit more would be more difficult. I'm always guaranteed if I'm sorry to keep flipping back and forth. I'm looking for the best expression for it, and I think it's here. If I look at this expression for the power spectrum, then I notice that if I integrate over a unit interval, that I'm always guaranteed to get 1, always, because this term over a unit interval always integrates to 0. If I chose a different kind of value for the symbol sequence, then this would be different, and I would find the correlation functions. There would be something in the denominator would be a little bit uglier, but you could do it. You could do it. I just preferred to have it nicely normalized, and I think that in the physical case, this is also going to be what we will find physically. Have I kind of maybe sort of? I'm intrigued by this. I think some of your suggestions are good and they're interesting to think about. I do not have a good answer for you. I need to think about it more. Yes.
You looked at changing the weights instead of 50-50.
Oh, have I looked? So instead of having it be a half and a half, I could look at 3/4 and 1/4, something like that. I have not. Now that is a very interesting suggestion. It would still keep the same architecture, but change the frequencies.
Part of the
change the probabilities.
You have like period 1.
Right. So if I chose this to be, if I chose this probability to be 0 and this probability to be 1, then this guy would just be a bunch of zeros. And if I chose it the other way, such that this were 1. So the probability here were, the probability here was 0, and we just got rid of this arc, it would go 1, 1. It would do the same thing with 1s, which is kind of curious. So it looks like it has this, both limits. It does. To answer your question, I have not, and that would be an interesting thing to do. Absolutely.
Like this, and then the other plot, you really have 2 features.
Yes.
Is that probability, do you tune to get more of one feature?
It would be absolutely interesting to draw a family of these power spectra as a function of some parameter that for the probability here. That would be, and see how this guy changes, because we know the limiting values is going to go to just a pure point here at 1, and it'd be interesting to see how it gets there. That's a very interesting question, and I do not know the answer. I have not done that. Everything I have shown you up to this point can be done much more nicely using Z transformations, and can be done much more compactly. It's much more elegant. It is a much improved formalism for actually doing it. And many of these things can be written down analytically. I've shown you calculations where I've just literally written out the sequences and done the calculations, but you don't need to do that. If you use a Z transform, you can do all of this analytically, and it's very nice. Paul has done some very nice work with that, and I actually wanted to borrow some of it. But before I leave this slide, I want to talk a little bit about this guy right here. Now, if we look at this, you might think, okay, well, look, it has a little bit of a wiggle there, I don't know what that wiggle is, Should I be concerned? Is that a wiggle? Is there something there wiggling? What should I? Well, let me tell you a little bit how I calculated this. So, this is a very long sum, and it turns out to be sensitive to little variations out here, even for large n. So it's important that this actually go to the asymptotic value when you calculate numerically the power spectrum. And so I actually force it to go to its asymptotic value when I calculate the power spectrum. I make it happen. I don't give it an option. I use, however, the first few correlation functions to are actually just numerically calculated, and then I have a cutoff where I do this. In all of the examples I'll show you today, except for the next one, I've chosen that cutoff to be exactly 10. I've made no attempt to try and make this guy nice and smooth. In other words, I've not checked that at 10 whether there are still little oscillations here that you can't see, and those little oscillations turn out to be important. So the numerics here turns out to be a little trickier than you would think. Turns out you have to be careful about that. And the answer to this question is, Paul has actually calculated this guy analytically, and if you look at Paul's spectrum, you'll find that there are no wiggles here. It's nice and smooth, it's nice and monotonic. It doesn't have this little dip and this little jump. And on the other side, well, these have to be the same because of the nature of the power spectrum. But you don't get that. This is an artifact of the calculation. So it's nice to be able to get rid of that sort of thing. And so a Z transformation allows you to do that in a very nice way that these numerics don't. I purposefully did not try to get rid of this wiggle just so that I could mention this. When I've done other power spectra that I've tried to publish, I've generally played around with this cutoff to try and eliminate these frequencies that seem unbalanced. And that is a pain in the neck to do. Very, very, very unpleasant. Guessing the right one. And there's a little bit of an art to it that gives you pretty good results, but sometimes it's really hard to get rid of these. So an analytical way to do this is very practically, is really quite useful. Before I leave the even system, is there anything, I know you thought a lot about this. Is there anything you wanted to say, Paul?
I think you've covered it nicely.
I wouldn't say that, but so the next process I want to talk about is Thue-Morse. So Thue-Morse, as we mentioned, is not like the others. And when I immediately look at the power spectrum, I can see that this certainly does not look like the others. Let me just think about the powers. Listen, what is the Thue-Morse sequence? I'm not sure you've talked about it, but maybe I should remind. Okay, so I start off with, let's say, a 0, and I do the following mapping. Everywhere I see a 0, I replace it with a 0, 1. So my first iteration would just go from 0 to 0, 1. Now I have a 0, 1. I do this mapping over again. Everywhere I saw a 0, I now put another 0, 1. So the first is a 0, so I get a 0, 1. And then the last for this previous iteration was a 1, so I now get a 1, 0. So if I go to the next iteration, the total sequence is 0, 1, 1, 0. And then I just keep doing that over and over and over. And if I do that, you can see this is a highly structured process. First of all, there's no entropy involved in this guy. It's completely deterministic. It's just highly structured. It turns out that this is the only power spectrum I'm going to show you where this is done, but I've taken the log of the power spectrum on the vertical axis instead of just the absolute value, and that's because I wanted to show you this, and if I did it in terms of a linear scale, I wouldn't get this. Notice that this goes over, 8 orders of magnitude, and it can change fairly quickly, going over, these are small changes in frequency, and, since this is logarithmic, this is huge variations that one is seeing. The next thing that's interesting to look at in this power spectrum is that if I look at this guy right here, now you have to sort of want it to be that way a little bit, but if you look at this, it sort of looks the same as this. So this guy, it's not exact, but it sort of has a fractal-like character to it. And if I were to magnify and look at smaller and smaller intervals, I would again find that I get structures that are self-similar in a sense. When I calculated this spectrum, I used 1,024 symbols and created according to this mapping, and I used 1,000 points to calculate this power spectrum, as I've done with all the power spectra. But if I'd used a longer sequence, that I could have gotten more and more structure here. So if you use a very long sequence, you can actually see quite a bit of structure, and it gets it gets unplottable because these ups and downs get so close together that you just can't, it just looks like it's a band. Yes.
So just to clarify what the sequence actually is if you have two bits, then it's 0 and 1. If it's 4 bits, then it's 0, 1, 1, 0.
Can I over here? So let me do it here. So I start off with, let's say, a 0, and then I use the mapping. 0 goes to 0, 1. So then my next iteration. So this is, let's say, the 0th iteration. Then this would be the first iteration. The second iteration, I would just take this 0 and map it to 0, 1. 0, 1, so that this guy does that. And then this guy, I would just take this mapping, 1, 0, and this would then be, then I just keep doing it over and over again. So, a couple of things. This guy forbids. You'll never see this sequence. This is forbidden. You'll never see 3 symbols that are the same in a row. It forbids a lot of stuff. It's very structured in a way that is a little kind of intimidating for me, frankly.
We have seen this before. This is the symbolic dynamics of the logistic map of the concept of chaos. Now, correlation functions are equally interesting. We look at these guys, and I went out to 100, and I cut that 0 off. But in the other graphs, you'll recall, I went up to, I think it was 30. I went up to 100 just to show you that I wasn't cutting it off prematurely. In fact, this guy never settles down. It just sits and just fluctuates. You can go as far as you want. It just fluctuates, and it doesn't repeat itself. It has no, you can't approximate it with some type of something ordered that you can calculate. It just bumps around. You can see that it's not completely random because these guys right here, the same. looks like order, and this does too. Why would they all be the same values? Clearly there's some structure in it, but it's not any structure that one can write down analytically. So the correlation functions look pretty funky. Those correlation functions look very funky to me from correlation functions that I'm used to seeing. We will not attempt at any point to try and reconstruct this process. This process is not something that we can write down as a finite order process, and there will not be any way that we can, I know of no way where I could find that. If you were to give me this spectrum, if I didn't just recognize it, I couldn't tell you where it came from or how it was created. I could give you no insight. This also scales. It's not only fractal, but it also scales. I don't know what the power of n is, but it's between 1 and 2. So it scales very, very funny. It doesn't scale like the other diffraction spectra did. This is a weird dude. This is very weird. Now you might think that, well, if you're really ultimately interested in materials, why would you even be worrying about this? Well, people make materials that have that have two and more structure in them. And when we talk about materials on Thursday, I'll give you some idea of what I'm talking about. You can actually construct materials and put this in. And in fact, when you do that and you calculate the power spectrum, or you let nature calculate the power spectrum for you, you do get this funky spectrum. It's certainly real. So you can see this, but you don't typically see this in just your average run-of-the-mill material science. Questions? Power spectra, they're kind of fun. They're kind of a little addictive when you start looking at it. Sir?
You talking to me? I have a question.
Oh, please, please.
Okay. So it seems like the funny, or a comment maybe, it seems like the funniness in this power spectrum and in the sequence we get out is because we're analyzing it in the wrong way, right? It's constructed in a very simple way by sort of, I don't know, peering down at smaller and smaller levels, but we're analyzing it from the left to the right, right? So we got a sequence and we're sort of analyzing it in a way that's, you know, different from the way it's constructed. So it seems like we could get a very simple output or a very simple either frequency spectrum or something if we try to analyze it in a different way. Do you have any thoughts on that?
Well, I mean, the frequency spectrum is what it is. I mean that's just. I mean, there's nothing magic about that. And if you calculate a power spectrum, you're going to get this. Now, you might ask, is a power spectrum the appropriate tool to use to evaluate this type of structure? And the answer is probably no, probably not. I mean, it's interesting to see what it looks like, but you know, if I saw this, I wouldn't try to analyze this to figure out that I got it by doing this. And you're right. So in some sense, I mean, this is a very simple mapping, and it does give rise to this very complicated kind of looking thing. And, you know, sometimes simple rules lead to very complex looking behaviors. And that is an interesting lesson to learn, that this guy right here wasn't all that complicated to write down, but we do get something that looks ugly. And so when we see things that are ugly in nature that may look like this, and you might see that if you're an experimental physicist and try to grab and pull your hair out, because my God, what is it? Then you might think that, well, there could be a very simple explanation for it. That would be my take on it. Certainly. I just want to go through this very quickly. It always seems that I talk more than I should. Power spectra are related to 2-point correlation functions. They're insensitive to third order, fourth order, fifth order correlation functions, which is interesting. They throw away the phase information when I calculate the Fourier transform, as we discussed, and so they lose information. The process of finding the power. When I find the magnitude of the Fourier transform, or the square is the power spectrum, then it loses information. Power spectra can be classified by their scaling behaviors. There were 3 kinds that we saw that I talked about. It turns out that pure point and continuous are going to be the ones I'm going to deal with from now on. This singular continuous is truly a nightmare. But these can have, as we saw in some of the examples, I can have pure point and continuous in the same spectrum. That just different parts of the spectrum can scale differently within. And that I've tried to give you some type of understanding of what looking at the power spectrum can tell you about the statistics of a sequence. So now my question is this. Suppose that we go back to the original slide, and you can't see the little zeros and ones. All you have is the power spectrum, and this happens. This experiment that people have been doing for about 100 years now. It's called X-ray diffraction, for example. Can you look at that thing, that power spectrum, and try to infer what the statistics of the stacking is? And the answer is, for a lot of stuff, you can come pretty close, but you can't do as well as you'd like. So this is something that Jim and I and another collaborator of ours from some time ago, Jeff Canwright, worked out, and we call it epsilon machine spectral reconstruction theory. And let me just go over how we do it. So if I have a power spectra, when someone hands me a power spectra, what they're really handing me from my point of view is a correlation functions. That's what I have. They've given me a bag full of correlation functions, because the very first thing I'll do is Fourier analyze that puppy. So I have access to the correlation functions, but I know that if they're underlying, that if there's some type of a sequence that I'm trying to reconstruct, well, the first thing I know is that sequence has to obey the rules of probability theory. And this is just a simple statement of the rules of probability theory. For any sequence U in a binary alphabet, this has to be true. The next thing is that the sum over all sequences of a given length has to equal 1. Probability is normalized. I think y'all are pretty comfortable with that. I'm not on shaky ground here. And then finally, this one you have to sit down with a little piece of paper and pencil and write it out and work it out to feel good about it. But it turns out that the correlation functions are sums over the probabilities of sequences. And the sum looks like this. I will work out some examples and show you and let you see where that sum comes from. And finally, I want to invoke another fact that has to be true. And the easy way to see that this is true, I wanted to find something called Q infinity. Let's assume that the sequence, unlike the two-Morse sequence, let's assume our sequence, our correlation functions go to some asymptotic value. And in nature, this happens. We see this. This is very good. This happens frequently. It turns out then that if I get far enough away, the process essentially loses its it becomes unstructured in the sense that the spins are not carrying any positional information anymore because the correlation functions aren't changing. And so the probability of seeing two symbols that are the same are just going to be the probability of seeing a 1 here times the probability of seeing a 0 times far enough away seeing a 0. Just those straight probabilities, and then conversely with a 1. So I can write down this relation, and that's just what I said in words. It turns out in the material science case we don't use this constraint, but because of reasons that I will explain on Thursday, but it still exists. We refer to these set of equations, forward, the conservation of basic rules of probability theory, conservation of probability, and relationships between correlation functions and probability. We refer to these as spectral equations that are given R. So what we do is the following. We say, okay, let me pick there to be a certain R, and let me pick it to be R equals 1, let's say, and then I write out these relations for R equals 1. So U is just going to be either a 0 or a 1. This means that omega here is going to be over the alphabet of 2, which means that omega here is now going to be either 0, 0, 0, 1, 1, 0, 1, 1. And then I use whatever, I use as many of these Q's as I need for a complete set of equations. And I may need to use more than I like. And then for the R equals 1 equations, I just follow those simple prescriptions, and this is what I get. Conservation of probability or normalization of probability. This is just one of those probability U equations written out. And this is just what Q1 is. So Q1 is the probability that two symbols that are a distance one apart, which means they're right next to each other. Two symbols are right next to each other. What is the probability that they're the same? Well, that's just the probability of a 1, 1 plus the probability of a 0, 0. And then finally, this last guy is Q infinity, which I showed you. So in fact, we can solve this equation. We have 4 unknowns, we have 4 equations. One of them is a little bit unlinear, but we're men, most of us, all of us, we're men inside, if not, and we can solve equations. We can do it. Okay, so the R equal 2 equations, not quite as cute, not quite as lovely. Let me go through it real quick. Writing out the first the first of the spectral relationships, I get these 3 equations, and these are the only ones that are independent. I can actually write out a lot of those equations, but they're not all independent, so I have to be careful to choose independent ones. This guy right here, in fact, just conservation of probability, no problem. And then finally, I write out Q1 and Q2 and Q infinity. They look like this, just straightforward application of what I've done, but I only have 7 equations. Unhappiness. I need another constraint. So what do? I do something that we're going to call memory length reduction. And that is, I write out what Q3 is, but Q3 now depends on sequences of length 4. But if I'm solving at R equals 2, I want to solve for sequences of length 3. So I need to somehow rewrite sequences of length 4 in terms of sequences of length 3. And when I do that, what I do is I apply this kind of reduction where essentially when I go from this step to this step, I forget that there's a history of 3 here, and I approximate it just by a history of 2. It's at this point that I'm essentially evoking a Markov approximation. I'm forgetting that I could have a longer memory. And when I do that, I now get the probability of sequences of length 3. So I rewrite this guy, probability of sequences in length 3. It's a straightforward, if not tedious exercise. And I now have another equation that we can solve. Great. You might wonder, well, R equal 2, this was a little bit, not too bad, but can you do this forever? Well, the answer to that question is no. But I'll get to that in just a second. So let me just tell you I got ahead of myself, sorry, the algorithm. So that represents eMSR. So what we're going to do is we're going to take a power spectrum and we're going to find the correlation functions. Then we write out and solve the spectral equations for sequences of a given length. Once we do that, we label candidate states by their length R histories. That is, if I solve for the sequences of a given length, that should probably actually be R, well, solve for R equals 2, and that should be R minus R equals 1 histories. If I solve for R equals 2, then I know the probabilities at the end for probability of 1, 1, probability of 0, 1, probability of 1, 0, and probability of 0, 0. Those are my 4 length 2 sequences. I then assume that this causal state structure is technically it's called first order Markovian, but I assume I can label the states by the last symbol seen. So I assume that I can do it just like the golden process looked, that I can label one state as the last symbol seen was a 1, the other state, the last symbol seen was a 0, and and then I write down all the allowed transitions that I can get going from that so that it'll be Markovian. And that is at this point that I impose a causal state architecture on the process. You might find this, I find this, and I would suspect that you do, a little bit, it goes rather against what you would hope to do in computational mechanics. You want, for example, the process to tell you what the causal state structure is rather than you impose some structure on it. And we'll talk about that just a little bit in just a little bit, but that is an issue. That is an issue. Again, so we do the merging just like you do in regular computational mechanics, and then once we've from here on, we just use our candidate epsilon machine or our reconstructed epsilon machine to calculate correlation functions in power spectra, and then we compare it with the original correlation functions in power spectrum to see if you get the same thing that you had, in terms of correlation functions in power spectrum. And if we don't get sufficient agreement, and however you wish to choose to define sufficient, I'm going to leave that very vague here, but there are natural ways to choose to define this. If you're not happy with your answer, you can increment and do it for a larger R. Now, back to a question that I asked earlier, and that is, how large can R go? Well, at R equals 2, we had to go up to Q equals 3. There were 8 equations, and the maximum number of terms in any equation was 8. Not so bad. R equals 3, I have to go up to Q is equal to 7. But Q of n equals 7, not bad. The number of equations doubles and is 16, and the number of terms in the very last equation is 128. Again, that's very doable. When we start looking at 4, we see that it's this column that becomes kind of annoying. That in order to write these equations out, that we get equations that have just a huge number of terms in them. This is certainly doable, but you're going to have to teach a computer how to write out those terms. But it's very algorithmic. It's straightforward to do. But if you get to n equals 5, you get that there's a billion approximate terms. And so at this point, somewhere in here, you're going to give out a gas. This is growing as the exponential of an exponential, and that is not scalable in today's world. That's not going to be ultimately scalable. We hope that there's a better way to do it than this reconstruction process, because this says that we run out of gas. I don't know how much time I have, but I'm guessing I have very little. Oh, I'm fine? Oh, okay, wonderful. Wonderful. Questions? I'm that clear. I often surprise myself. So let's do a couple of examples, and some of the examples that we've looked at, I'll show you what you do when you do. We call epsilon machine spectral reconstruction. We call it eMSR. So I want to treat three processes. One is the random, the golden mean, and then finally this infinite range process, this infinite memory process, if you will, the even process, and see how close we come. Well, so I have done the emissary algorithm, and I'm not going through all the details for you, but they're straightforward, like I mentioned, and I'm happy to go through them if someone would like me to. We find that we nail this puppy to within numerical error. No problem. No problem. Of course, this wasn't a really challenging exercise. If we couldn't get this one, then we would know that we had a problem. But it's good to know that we get the flat correlation functions and we get the correct power spectrum, and so life is good. But this was an R equals 0 process. This was a process that had no memory at all. So this wasn't really a very good test. But we did, but we passed. And I prefer to think of success in terms of whether you pass or fail and not how hard the test was. That's just me. The golden mean process. Now remember, this was an R equals 1 process, so I should also be able to do a good job here because I can write out the R equals 1 equations, I assume the appropriate causal state architecture, and see what I get. Well, once again, I'm doing very, very well because, I'm really nailing these guys. I get all the correct probabilities. When I calculate the power spectrum from these correlation functions as I did before, I find that I do very well. I've got these little wiggles down here. Again, this is numerical stuff that the Z transformation will just get rid of. And I'm a little bit troubling. I'm not quite getting this little peak here as nice as I want. I want to go back and check the numerics on this, but it's still very close. But it's not. That's a tiny bit troublesome. I really should get the exact answer, pretty close to the exact answer. So I didn't even write down these processes because you know what they look like. We showed them to you before. Yay, we're done. Okay. What about an infinite memory process? And you might say, well, you're interested in materials. Materials? How can you have an infinite memory in materials? Materials, I mean, what happens here is generally affected by what happens next to me, or maybe 2 or 3 away, but it's certainly not very, very far away. In fact, Jim and I looked at a simple model of transformations in zinc sulfide, and we found that the kind of that these guys can essentially invoke an infinite memory. So thinking about what infinite memory, thinking about how emissary works with infinite memory processes is actually very relevant because we think this is probably pretty common in nature, and it's important to see how well this algorithm will capture it. So this is not just a fun intellectual exercise. This actually is quite meaningful. So here's what we do when we do the even process. Not as good. Not as good. It turns out that I've done this for R equals 1, and it turns out that I'm missing these correlation functions right here. I'm missing these guys. I get the first one, and I get the asymptotic one, and those are the ones that I use to recreate this process. So I got those, but I'm missing these guys right here. The causal state architecture looks like this, and remember, with the even process, we were forbidding. I wrote it down so that we were forbidding zeros, an even number of ones. Those here, all sequences are allowed. This forbids exactly nothing, and so this is just. You can see symbols of arbitrary length are allowed with a non-zero probability. So we're missing a lot. But then again, we chose a bad architectural structure, and when we do the machine reconstruction, I don't think we can be happy with that. I certainly am not. So I say R equals 1, not good. Let's go to R equals 2. R equals 2 is going to be the green. And let's look. The first thing that you'll notice is that, first of all, solving the equations for higher order R's is not that trivial. The problem that you face is this. That when you write down a probability and you want to find out the probability of a symbol sequence, you want it to be a real number between 0 and 1. But when you solve the spectral equations, you're not guaranteed that that's going to be the answer. I mean, the spectral equations have nothing built into them to guarantee that. So what we do is we try to find a set of probabilities that best satisfies those equations, and even though it may not satisfy them as well as we would like. And what happens here is that it's hard to satisfy the spectral equations, and we in fact miss this guy by just a tiny bit for the asymptotic value, and we get the green here is pretty good for the first two, and not so good for the third, but you know, and then it just kind of does this. So it's better, perhaps. I mean, just qualitatively looking at it, I might argue that it's better, but it's still not, you know, fabulous. If we look at it over here, we find that, well, it looks like I'm tracking it a little bit better. I'm getting deeper into the lows. I'm overshooting here at 1 again, which is really weird, but you know, in some ranges, looks like I'm following it more closely than the R=1 approximation. So at some level, I might say, hey, you know, it looks like it's better. Just qualitatively speaking, it looks like it's better. Looking at the causal state architecture, I find out that this is the R=2 machine that I get. This machine forbids exactly no sequences. It allows all possible sequences of any length with a non-zero probability. It is, so we know that we're missing something kind of fundamental to the even process, the fact that you can't see an odd number of ones. I mean, I don't have a whole lot to say. It is what it is. It's not terribly satisfactory. There are a couple of comments I'd like to make, though. First of all, you might assume that looking at S0 and S1, that since they both have the same probability of seeing a 0 and a 1 out of these, you might say that we can collapse these two into the same causal state. But in fact, we can't, because we want to look ahead not at length 1 sequences, but at length 2, since the spirit of this epsilon machine is really looking at memories of length 2. And it turns out that the probability, let's say, from this sequence to seeing a 1, 1 is 0.65 times 0.65. And the probability from this causal state is seeing a 1, 0.65 times 0.78. So S0 and S1 do not have the same features to length 2. So there is no collapsing of causal states here. As you might like. The next thing to notice, and I have to tell you this because it's not obvious, when you solve the spectral equations, there's not a unique solution. There are symmetry-related solutions. And in fact, I could replace all the zeros by ones, and this epsilon machine would give me exactly the same diffraction pattern. And that sort of makes sense, because if we go back and we think about the power spectrum, when I wrote the power spectrum in terms of correlation functions don't really know whether it's, but by the time I write it in terms of correlation functions times the cosine term, it doesn't really know whether there's zeros and ones anymore. It only knows the probability is same or different. So the power spectrum itself is insensitive to whether it's a 0 or a 1, and it turns out that all the approximations are also insensitive. If you solve this equation, you get 2 solutions, not just 1. And the second solution corresponds to replacing all these 1s with zeros, and the zeros with 1s. But of course, physically, that doesn't matter. I mean, one solution is just as good as another, and if you have an arbitrary, you know, if no one told you that some symbol had to be a 1 and you know, and there was the 1s and the zeros, then you wouldn't really know. You would have to use some other kind of information to get it. One should really do this for R=3 to see how far it can go and see if you can pick it up. R=3 should be important because at R=3, let's see, we have, so we have this sequence which should be forbidden, and at R=3 we'll have to use correlation functions that involve this sequence which should be forbidden, and it would be interesting to see if it does. This sequence is not forbidden in our reconstructed epsilon machine, and it is in the original process. So we should feel some, I mean, it's certainly progress, and certainly making some good, you know, college try, but we are missing some stuff. We are missing some stuff. So, questions?